Before Volodya starts, I would like to say a couple sort of personal words. Well, though I am in strong opposition to the current war, and I was not sure whether we should continue our sessions or postpone them to better times, but eventually I decided to continue because doing and discussing mathematics is a completely natural thing, such like eating, breathing, and so on. So we shall continue as long as we can, and we'll shall observe what will be happening. Now, that's all. I'm glad to announce our today's speaker. He's Vladimir Rubtsov from the University of Angers. You see the title, though the handwriting is not very clear. Anyway, Volodya, you're welcome. Please proceed.
Okay, so I shall start with a short speech, if you want. I'm completely on the same side like Joseph, and about the annulation or cancellation of mathematical events, I'm completely against it, in spite of support of what Joseph said. And even the first 2 weeks, they were really shocking, and many seminars were canceled. For example, we canceled our seminar in Thursdays. Tomorrow we will have no seminar in topological recursion. Last week we canceled it, and this week we canceled it. But we sent a letter that we don't want to give up, and we will continue next week with new talk in our seminar, and our slogan is definite: make math, no war. So that's my talk. And then I propose you to be courageous and strong and continue the seminar. Moreover, I want to say that I'm pretty sure that my talk today is so might be very, I would say, long and not very well organized. So I can maybe, if you want, I can continue next week. If you are, of course, if you are interested in, because when I prepared my talk, I didn't succeed even to cover all things announced in my title. So I will speak about kernels, but I will not speak about multiplicativity, and non-abelian meaning of Abel's theorem will be only touched, and also the question around. I suppose that there are many other questions around. Today I'm able to speak only about few. The subject is very
I'm sorry, stop, because you concerning the procedure, you told that the talk will be long, so let's agree on the following. We have for the next 2 sessions, we have already the program. It will be Mitya Alexeyevsky and Valia Lchagin. So let's agree on the following. You
okay.
You just wait. You will tell us as much as you can during the standard time. I mean, approximately
I'm sorry.
And we can proceed well after the planned talks will have place. So we shall proceed in April. Is it okay, or will it be maybe it will be 13th of March? So we shall discuss it later.
Okay, yeah, I'm terribly sorry, Joseph, because it looks like I was very aggressively proposed to.
Yes, yeah, I know that you are very aggressive, but well, I got used.
It is first of all, I'm not sure that you will like what I'm speaking about, because it is not a typical subject of the seminar. But of course, you will see a lot of differential equations.
Okay, so Volodya, we shall discuss details later. Now let's begin your talk, and then we shall decide how. But do not be in a hurry. We shall find time for continuation.
Okay, thank you.
So thank you.
Thank you very much for this invitation. And I want to repeat that in this time, it is just absolutely important to make math, absolutely important. Otherwise, you can go crazy very, very quickly, which was happened with me with the first 2 or 3 days of this horror. And I'm not sure that I'm completely came back. Okay, anyway, I will speak about multiplicative kernels, whatever it means, non-abelian Abel theorem, whatever it means, and around, which is clear. And this talk, it is in fact a result of some ongoing project which started long time ago. We started with Vasily Golyshev and Anton Melit in 2011. And then it was very, very slowly developed, stopped, again developed. Then we discussed with Maxim, and then Kontsevich, and Maxim gave some input, but didn't continue to discuss. And then we came back to this project with Duka van Straten and Ilya Gayur, who, you know, this young guy who is in Birmingham now. And my talk will be based on a paper with Golyshev, Melit, and Van Straten last year in arXiv. This paper is a terrible example of just program paper. No good, I would say, explanation, no good motivation, just examples and prospect how these examples can be used. I'm afraid that my talk today will be not very different in style. But the subject is so beautiful. You will see that so many beautiful things. I am not able to, I would say, I have no courage to hide from you this beauty. Even there are no theorems. There are many numerical experienced numerical computations, which mainly were done by Ilya Gayur, but these results are practically confirm beauty and fruitfulness of this consideration. So our motivation, we have many motivations. First motivation, it was not mine. It was motivation of Duka and Vasily, who came from the so this crossroad of differential equations, number theory, algebraic geometry, and even at the end you will see some algebraic topology of 60s, 70s. But from the viewpoint of number, and also of course from string physics, because many things are inspired by so-called Calabi-Yau mirror, Calabi-Yau-Landau-Ginzburg mirror correspondence. So motivation of my colleagues from number theory is the following. I will speak briefly and introduce some actors of the story. So a few years ago, it was, I don't remember how long, maybe 10, maybe 20 years ago, probably even 30, number theories, Donzagier and French mathematician Apéry and Frits Beukers from Holland, they gave a list, a classification list, very special second-order differential equations. These second-order special differential equations, they have beautiful property, and you will see that some of them are appeared in this Calabi-Yau mirror correspondence as equations of so-called Picard-Fuchs for period of Calabi-Yau varieties. What these equations are? Generally speaking, these equations are the following equations: L. They have degree n. And theta is a logarithmic derivative which people use in number theory very often. Instead of d over dt, they consider t d over dt. So this theta will be everywhere. And then you have polynomials, p1 of theta, p2 of theta, polynomials in front of the terms degree 1, 2, r. Each polynomial p sub I of theta, they are polynomials of degree n. And these polynomials supposed have very good monodromy properties. They have so-called MUM property at the origins. And this MUM property means maximal unipotent monodromy. This maximal unipotent monodromy implies many interesting things. For example, a special structure of base of fundamental solutions. We shall call such operators very vaguely. It is not very completely exact Calabi-Yau type operators or Calabi-Yau operators. So this equation, as I told, arises as the equation on periods of Calabi-Yau varieties. Let's consider more precisely what does it mean. If we have a Calabi-Yau R-fold variety of dimension R, then we have a top holomorphic form, R form, omega sub R, nowhere zero, and then the usual Gauss-Manning connection theory, which I don't want to remind. If you are interested in it, it should be a special story about it, implies that periods of this Calabi-Yau, and it is also very precisely defined notion, this function of periods, which defined by integration of top form over some cycle gamma, depending on the parameter t. So it's a family depending on t, satisfies so-called Picard-Fuchs equation. Let's consider this just an example. For r equal to 1, it means for one-dimensional Calabi-Yau, and there is only one-dimensional Calabi-Yau manifold, it's torus or elliptic curve. So we have a family of elliptic curve. I will choose for simplicity just this Legendre form of this elliptic curve. So we have elliptic curve given by this Legendre model. And this one-dimensional Calabi-Yau family has the following equation on its period. So its period phi can be very, very explicitly computed. It is elliptic integral, famous elliptic integral. And it is a solution of the following second-order differential equation with a special type of singularities. As I told you, at the origin, t equal to 0, this operator has maximal unipotent monodromy. If you have r equal to 2, it means you have surface, the Calabi-Yau surfaces, there are two types. One type I will not touch, it is just torus, and second type is the so-called K3 surface. We spoke about K3 surfaces, at least people who attended my talks. I very, very oftenly spoke about K3 when I spoke about elliptic algebras or about geometry of Monge-Ampere equation. But here I was also I'm sure that I need to speak about case 3 because this corresponding Picard-Fuchs equation of periods of lattice of this case 3 surface, it's differential operator of order 3. For example, very typical quartic K3 surface given by equation of degree 4 in P3, it is a typical example of so-called dwarf family of folds. So this is a variety twofold, that's it's a surface. And the corresponding Picard-Fuchs equation, it's equation of degree 3. So you remember that theta is a t over dt. So you can write the equation on the period in this form. Look, this form is quite special, but it is typical form for all Dwork type hypersurfaces, because Dwork general family, it's for for any degree of polynomial, so even for 5, for 6, and etc. And all Picard-Fuchs equations, they have very similar type. So if we speak about threefolds, for threefolds, we have this again typical Dwork family. It's a quintic in P4 in projective space of dimension 4, and the corresponding Picard-Fuchs equation, you see, it is very similar to quartic in P3, in quintic in P4. Picard-Fuchs has the following operator: theta 4, 5 times t, 5 times theta plus 1, plus 2, plus 3, plus 4. Very similar. At the moment, I will stop about, because it was a motivation. At the end, if I have time, I will go back to this, because what I will find, and I will show you some beautiful relation between absolutely different story with this Picard-Fuchs Calabi-Yau equation. I just want to warn you that my talk, it is a kind of a mosaic of results which some of them we don't understand now. We just fix them, their beauty, but we don't have any conceptual, I would say, explanation why different and beautiful results appeared in different and absolutely, from the first glance, far branches of mathematics. So don't ask me why, because we just fix something and we don't know why. Sometimes we know why, but it is just we are in the first stage of our project. I will start with the second motivation, which came from very, very classical, I would say, elementary notion of so-called addition laws. And I will speak about Abel theorem in abelian case first. So what are addition laws? The simplest addition laws you know since your school time, and it is just a sum of logarithms, which is equal to logarithm of product of this expression under logarithm. You can write it in integral form. If you take the differential one form on R star with parameter t, with coordinate t, and usual multiplication, then this multiplication, this additional law is multiplicative. In fact, it is not addition. You can speak about sum here, but you have this product. But you also can consider just one form d of u on full R, not non-zero, and you can interpret in this elementary way just addition law. So you have sum of integrals, and it means that sum of limits equal to limit of the sum of integrals. More interesting and also known to you since school time, it's so-called Euler formula. Euler formula. I will start with the elementary formula of sine of sum. Sine of sum, you know, it's a sine of u cos v plus cos u sine v. Cosine you can express as a square root of sine 1 minus sine square, and then this formula gives you this expression completely algebraically one through another. In integral form, it means that you have integral from 0 to x of this arcsine primitive, and then you have sum of two integrals, and it means that the limit of the sum gives you algebraic expression in terms of x and y, and it is a sum of arcsines gives you this arcsine of this z. More interesting, of course, also Euler, it was very, very old result in 1750, so-called addition law for elliptic functions, which are entered in elliptic integrals when you try to compute the length of arc of lemniscate curve. Then instead of square, you have degree 4 on the square root, and sum of these two integrals gives you the following beautiful expression for this z. This z equal to algebraically this rational function, and here the x square root of 1 minus y4 plus 1 minus x4 divided by 1 plus x2 y2 2. I think that it is, everybody knows this, but it is anyway, it is absolutely beautiful. Now the next step was done by Abel in 1828, and Abel generalized this Euler approach in the following way. I just want to, before I go to this, I hope that this elementary reminder is not very abusive. Do you have some questions so far for this? No? Is it clear? Or I shouldn't be so elementary? Joseph?
Yes, Volodь, proceed, please. I have no question. If anyone has, he will ask it.
Okay. Okay. So the next step, it is so-called Abel theorem. There are many incarnations of Abel theorem, and Abel generalized these beautiful Euler formulas in the following way. He considered rational form omega r of xy, where dx. I'm sorry. I'm terribly sorry. I forgot dx here. I think. Yes, it's one form with rational r, and x and y are related by the equation some f of xy equal to 0. Geometrically, it is equation of affine curve, and implicitly we will suppose that y depend on x algebraically. Okay, and then what we call now hyperelliptic curves C. That was what Abel considered. He didn't consider a more general type of curves. He considered elliptic and hyperelliptic curves. And in these terms, his result can be interpreted in the following. You have this form omega, rational form, and you have integral over this from you have endpoints x1, xn, and then Abel said that there is such number p that for any number n bigger or equal to p, you can reduce number of integrals in this sum. Instead of considering the sum of n integral, you can consider sum of p integrals modulo some rational function or rational function of logarithm. So this function e of xy, it's a rational function or rationally dependent on logarithm. And
logarithm of what? Logarithm of what variable?
Hmm?
Logarithm of what? Logarithm of function of what? Of x and y.
It is rational function on x and y, and or it is logarithm of rational function of x and y.
Logarithm of x and y. Okay, thank you.
Yeah, and all these new limits, new points, y1, yp, they depend on x algebraically. Okay. Later, I will just go a little bit ahead and then come back to Abel theorem. Later, Jacobi and Riemann and Klebsch and many other people, they reinterpreted this for in the different geometric way. I will speak about Jacobi interpretation. So we consider this compact curve C given by equation f of x y equal to 0, and one form on this curve, and then this Abel theorem in terms of algebraic geometric terms can be reinterpreted like a linear equivalence of the following divisors. This linear equivalence of this divisor and this divisor. And it just means that the reducibility of number of integrals can be considered like a reflection of so-called Abel-Jacobi map, which is a map from symmetric and symmetric power of the curve to Jacobian of this curve when number p, which enter in this Abel theorem, it is a genus of your hyperelliptic curve. But this may be not very clear from the very beginning, but it becomes more clear if you consider genus one case. The classical Abel result, it is just, you can specify for elliptic curve, which I will write in Weierstrass form with two parameters, modular parameters g sub 1, g sub 2. And because the elliptic curve is a simple but abelian variety, then we can introduce geometrically so-called addition law on this variety. This addition law reads as follows. You have an elliptic curve and you have a secant line. The secant line. On the secant line, you find 3 points of intersection with your elliptic curve. And addition law means that the sum of 2 points, P1 and P2, equal to P3. So P3, it is there are two values. I take a positive value. And in integral form, this equivalence of divisors, if you want, can be expressed if you have the following one form on elliptic curve, dx over y. Then integration of dx over y between fixed point P0 and P1, P0 and P2, equal to the integral of omega from P0 to P3 modulo the lattice, which defined your elliptic curve, modulo gamma, modulo this lattice gamma. If P3 is a sum of these 2 points. So their collinearity condition, it's an addition law on this curve, and this is equivalence of this divisor. On modern language, you can say that this equivalence of divisors defined on the Picard variety with fixed point P0 of this elliptic curve. So set of all line bundles, the structure of abelian group. It means if we have a structure sheaf in P1 and structure sheaf in P2, the tensor product of sheaves gives you structure sheaves on P3 if and only if you have this collinearity of these point or equivalence of these divisors. So it is a essence of abelian Abel theorem. From the viewpoint of our approach, we it maybe naively consider non-abelian Abel theorem as an analog of this, but we replace the first order differential operators, which are appeared in this equation of simple equation, and line bundles or line bundles with connection. I will just show the simple example. And we want to come to any order differential operators and replace line bundles by vector bundles with connection. And we have some very partial success in this interpretation. Let's start with left-hand side. So we just suppose that we have one form omega, and we will think geometrically that it is a connection form in a line bundle. Then we have very simple differential equation with a very simple solution, which is exponent of this of integral of this form. And of course, we can consider product of this solution in the point x and in the point y. And this product is the product of exponent. And product of exponent gives you exponent with the sum of integrals. And of course, sum of integrals, it means that limits x and y gives you limit x plus y. So this equation relates to the simplest addition law, which I reminded you from the very beginning. But even in this case, we can write this product in the integral form with the kernel. Why we need it and why it is beautiful, it is a part of our point of view how to get non-abelian version of this. So it means that we want to write this product of solutions in two different points as integral of a solution in third point z with some function which we call the kernel big K of x, y, and z tz. And this, in some sense, it's a form of Abel theorem because we reduce number of solutions, we reduce number of integrals, and we have only one. Here we have two. Here we have only one, but we have some special integral kernel. In general, it means that if we have n points and the product of solution in n points, we can also we have a hope to represent like integral over this p variables of this product of solutions in less number of varieties y1, yp, and the kernel, which depends on nx and p variables of y. That's the philosophy. It's a general philosophy. And we will see that this kernel, sometimes it's a beautiful and very rich structure. First, let's consider toy models. The toy models are, even toy models are beautiful. So if we have first order differential operator with solution phi lambda exponent lambda x, then the product of phi lambda of x, phi lambda of y gives you a kernel after integration over z, gives you a delta function kernel. Whatever it means, yeah, if you don't like delta function, I will immediately replace this representation by a normal representation, and the kernel will have a very simple rational expression. How to get it? It is also very nice exercise, and I can't hide it. We take the products of exponent. I will take lambda equal to 1 for simplicity here, just not to put many lambdas everywhere. Let's take product of exponent, replace exponents by series, in x and y, and then we just make a very simple and elementary trick. We introduce new variable z, take the expression for z to m plus m divided by m plus n factorial. It will be future exponent of z. Of course, we keep denominator n factorial m factorial, and to change nothing, we divide by z times n and z times m. And also to eliminate appearance of m plus n factorial, we multiply by m plus n factorial. What we have? We have sum on m and n of this binomial coefficient m plus n n, x over z to n, y over z to m, and z to m plus n over m plus n factorial. And of course, you can immediately take summation considering the geometric progression with formal parameter x plus y over z, and consider this sum like a residue, like an integral over dz over z. This is exponent to z. It comes from this term, of course. And this, guys, they come from this geometric progression. And you take the coefficient over z equal to 0. So this, you obtain the kernel, which is when you just multiply by z, what you obtain? You obtain the kernel, which I promised you. 1 over z minus x plus y. There is a difference of sign because I was not very precise. And also, I want to say that there is a conjecture, which we didn't prove, but the conjecture that all first order operators, they have a delta function type kernel. And this delta function type kernel relates to addition law. And multiplication law kernel with delta function correspond to the operator x over d over x minus lambda with solution phi equal to x to lambda. So it's very easy to check, but we didn't prove it in general. Now, in the case of second order, the situation is even more beautiful and even more interesting. First, we want we may make very simple observation. We can modify this. We can modify this, and instead of function phi, like exponent, we can introduce the function g sub n of x, which different from exponent only this number n in degree of factorial. But this number n, it's a crucial difference from n equal to 1. For example, if you take n equal to 2, then this function is a solution of a version of Bessel equation. It's a Bessel function. And this n Bessel function, it is a solution of the equation theta to n minus x. This theorem, which for n equal to 2 is classical theorem, which known since 19th century, the product of this n Bessel GNX, it is of course our vague terminology n Bessel. It is an analog of Bessel, that this product of these solutions can be represented in terms of Gn of z with the kernel h sub n of x over z, y over z. Well, and we have the residue, so we have dz over z. We can replace it, and this h n kernel, it is just what? Sorry, this kernel, it is just this generating function with binomial coefficients in degree n, and x to m, y to n. In fact, x to n, y to m. But never mind it. It's just small. No. If it is n, then x should be n and y. What I want to say that this formula can be obtained, and this theorem can be obtained very easily from exponential product. Just you replace in proper place this degree n, and here and here and here, and then you exactly obtain this theorem. For n equal to 2, this generating function, for n equal to 2 has absolutely fantastic, beautiful algebraic expression. h2 of xy, it is 1 over square root of the following polynomial in x and y. And in fact, it's polynomial in 3 variables, x, y, and z. But here I put z equal to 1, and full polynomial in 3 variables. It's a fully symmetric quadratic polynomial. And if you consider its zero locus of this polynomial in projective space P2, then this zero locus defines a circle which is tangent to coordinate lines in points 0, 1, 1, 1, 0, 1, 1, 1, 0. Then if you change the variables x, y, and z by u square, v square, and u square, then this expression, this polynomial, can be factorized like u plus v plus w minus u plus v plus w, u minus v plus w, and u plus v minus w. And this, immediately you can recognize that this is nothing but the square root of Heron formula. This is 2 times p, this is 2 times p minus u, and etc. So this polynomial in u square, v square, and w square, it is 16 times square of area of the triangle with length of the edges u, v, and w. So this we will call such expression Heron configurations. It is interesting that such configuration exists for any n, in fact, for any n for such generating function. And you have algebraic expressions delta of x to n, y to n, z to n, minus fully symmetric expression and x, y, z degree n. For n equal to 2, this formula, which we write in theorem here, is known since 19th century, and this formula is called Sonnen-Gegenbauer formula. I admired this formula very much because I have found a very beautiful explanation of this formula in the old book of Naum Yakovlevich Vilenkin. In 1969, there is a book about special functions and representation theory, very old, but absolutely marvelous book of Vilenkin. And in this book, he explained all this beautiful geometry from elementary viewpoint. And it is very, very nice. Unfortunately, for n bigger than 2, it is not so it is beautiful, but not so beautiful like for n equal to 2. And of course, another important observation which we did, that this polynomial in xyz, this expression, it is so-called a partial case of Kontsevich polynomial families. I will go to explanation what is this Kontsevich generalized polynomial families. Let's consider more general second order differential operator, not so simple like Bessel operator, but let's consider the following. We fix for a moment a polynomial of degree 3, such a cubic, with coefficients a, b, and c, which will be our parameters. And then we consider the operator order 2, dfd plus t plus lambda. And this operator after transformation can be written like f times d square second degree or second derivative of phi plus f prime. This coefficient is always f prime, first derivative of phi plus t plus lambda of phi. So in the equation L of phi equal to 0. Then take solution phi of this equation and try to find the corresponding kernel for this product phi of x, phi of y, like we did it before, and phi of z, dz over dz, and integral over this kernel. The answer is the following. This kernel is the following. It's a b divided by square root of some polynomial p sub a, b, c. So it is a family which depends on these coefficients a, b, c, xy, b over z. And this polynomial b, a, b, c, which we will call generalized Kontsevich polynomial, this polynomial family a, b, c, it is a discriminant of the following quadratic expression. You have our cubic, this cubic, with this is a monic cubic with coefficient 1 in front of t cube. And we take a subtraction of factorization t minus x, so t minus y, t minus z. Then the principal term of degree 3 disappeared. You have a quadratic expression in t, and you take the discriminant of this expression. And this discriminant has the following form. It's a b minus xy, yz plus zx in square minus 4 x plus y plus z plus a times xyz plus c. First, we see that this expression is fully symmetric again. And of course, it's very important for some application. Consider special case of this cubic, so-called special Hoyne equation, which correspond to the choice of polynomial f, like t times t minus 1, t minus mu. So this singular points 0, 1, and mu. And this family of polynomials, this family of discriminant for Hoyne, we will denote by pm, p mu, x, y, z. Then I want to see the following observation, that this kernel in universal way depends on the choice of this cubic. And this cubic, geometrically, it is elliptic curve. Let's consider the elliptic curve u square equal to f of t. And this cubic is branched over their roots. And we can write on this cubic the addition law, like we did it before. So we have 3 points, p0, p1, p2. Their projections on this x, we will denote by x, y, and z. Roots are t0, t1, t2 of this cubic. And then the points, collinear points, gives you the addition law. And fantastic result about this Kontsevich polynomial, that this addition law are really, these addition laws for different polynomials are really gives very beautiful information about various mathematical things. For example, of course, it is just very briefly, I should describe the recent theorem of Ettinghoff, Frenkel, and Kazhdan. They considered so-called analytic version of Langland's conjecture I will not go into details, but I just want to relate it to our Kontsevich polynomial family. Let's introduce the following operator h sub x. This operator acts in some Hilbert space. I don't want to precise this Hilbert space, and function from this Hilbert space, one of these functions, just I denote, like in our case, by phi. Then this operator is defined as follows. We have action of this operator on phi in the point y. This operator is an integral with some coefficients of phi in the point z, dz bar, and this is a module of our Kontsevich polynomial, which correspond to this special Cohen operator with these four singular points: 0, 1, mu, and infinity. So why this operator is so important and so beautiful? First of all, Ettinghoff, Frenkel, and Kazdan proved that these operators h sub x, they are compact, they are self-adjoint, and for different x, they always commute. And they argued that this operator h x, in this analytic case, they have analogs of so-called Hecke operators over finite fields. And these Hecke operators were motivation of Kontsevich when he constructed this discriminant family. This discriminant family Kontsevich introduced to compute number of Hecke operators in the case of finite fields. I don't want to go to this details of this complicated for us thing. I just want to say that this is exactly the same operator for special choice of the cubic. And then I will probably go to my last part of today's explanation of beauty of these kernels and formulas. It's relation of these addition laws with the so-called Buchstaber addition laws in formal two-valued groups. I remind that if we have a commutative ring, then we have a formal group law. Formal group law means that we have a power series phi of depend on two formal parameters u and v in this power series with coefficients in this commutative ring. And the simplest example of such law is a addition law. So it means that the series starts with u plus v plus higher terms. And the second condition that this phi of u and v should be associative. It means that you have phi of u, phi of v, w for three variables. And it is the same like phi of u, v, and w. So it is an associative law. And if we have this formal commutative law, additive or multiplicative, I will go to another example, multiplicative. We will speak about two-valued formal group. For us, it is interesting to there are many different formal group law, but the most interesting are given by addition plus multiplication. This is a multiplicative or with some coefficients here, and also elliptic formal group law when this series phi of uv comes from elliptic integrals from Euler addition formula. Buchstaber in 1993 gave a very nice classification of some special type of algebraic two-valued formal groups. He considered so-called algebraic formal groups which obtained by very special polynomial construction from square of modules of formal groups whose addition law based on so-called Baker-Heiser function on the given elliptic curve. And he proved that all such formal groups, they are classified by zero locus of the following fully symmetric polynomial in 3 variables. Let's consider this polynomial. And you see that this polynomial very similar to Kontsevich, but not exactly, because Kontsevich polynomial, you remember, it was started from this discriminant. This discriminant, where it is, here. This discriminant is here. This is the xy plus yz plus zx. Here is the sum of roots. This is the product. Yeah.
I'm sorry, when I hear the words Baker-Hieser, I'm thinking about integrable systems. Does it relate somehow to them or not?
Well, not explicitly. It was Kontsevich who proposed how to generalize elliptic formal group law using Baker-Hieser function. Of course, this Baker-Hieser function, the expression of this Baker-Hieser function in terms of elliptic function, came from KP Baker-Hieser, of course. But you know, I want to confess that I don't understand how it links to integrable system. This thing. It's better to ask Viktor Matveyevich. Maybe he knows, and maybe next time when I will speak, maybe I will know as well. I will read it. Because
well, if you know something, please, well, do not forget. Okay, thank you. Please proceed.
So this polynomial, you see, it is a little bit different. It is also a kind of discriminant. You see this discriminant. This is a b square minus 4 times a c. If you have a quadratic trinom at square plus bt plus c, but the coefficients are different. It is in some sense inverse choice of coefficients, and there is probably there is some transformation. I tried to find a good expression for this transformation, but at the moment I didn't find yet. But I hope to find. What is interesting that in this classification of Buchstaber, you have 3 free parameters: A3, A1, A2. Sorry, A2. I'm sorry. A2, A3, and A1. A1, it is a value of Weierstrass P function in some point alpha. A2, it's 3 times P alpha square minus G2 over 4. And A3 is a result of Buchstaber. And A3, it is a 4 times P cube minus G2P of alpha minus G3 divided by 4. So you see behind of this, there is an elliptic curve, V square equal to 4 times U cube minus G2U minus G3, this elliptic curve. And there is a point alpha on this elliptic curve, which it enters, which enters as a parameter in all these 3 parameters. In all these 3 parameters, A1, A2, A3. Of course, my first question when I saw it, how it relates to Kontsevich polynomial. And for some special choice of alpha, it is indeed coincide with Kontsevich. So this transformation of discriminants has some identity. And this correspondence very explicitly can be expressed if you use recent Buchstaber-Veselov theorem in Russian Math Service 2019. They wrote the following very simple, in fact, by when you read the demonstration, but beautiful simplification of this classification polynomial. You take this polynomial f of x, y, z equal to 0, but you can replace this complicated polynomial by a very simple linear expression, just x plus y equal to z. big X, big Y, and big Z. How small and big are related? They're related in the following way. Small x, it's 1 over P over X plus P over alpha. Y, 1 over Py, big Y, plus P of alpha. And small z, it's 1 over P of big Z, P of alpha. And the corresponding formal group, it is abelian so-called coset group. It's a factor group of abelian elliptic curve, which is given by, with the help of these parameters A1, A2, A3. It is not completely this one, but it is a little bit different elliptic curve. Modulo involution V to minus V. So it is a isomorphic to P1. This formal group, it has very nice geometric interpretation. And how it relates to Kontsevich family, I discovered it myself, of course, because Kontsevich family was not known to Veselov and Buchstaber. Otherwise, it would be clear that they could did it immediately. So if we take all A1 equal to A2 equal to A3 equal to 0, it means that alpha is a 0 of P. I want to say that I made just a search how compute zeros of P function of Weierstrass. And I discovered that it is extremely interesting question, very recently discovered by Zagier and co-authors with a very interesting interpretation in terms of solution of hypergeometric equation. So these zeros of P function, it is a whole interesting world of differential equations, but differential equations of special type, hypergeometric differential equations. So if we have this alpha is 0 and G2 coefficients of this elliptic curve, which is just degeneration to this guy, then G2, G3 equal to 0. Then Kontsevich family with 0, 0 parameters. It is our Bessel expression, quadratic expression. It's our Heron configuration. And this, in the terms of classification of formal group law, it is just addition law. But we knew that this should be, in some sense, addition law. And from the viewpoint of algebraic topology, Buchstaber and Novikov, they discovered that this addition formal group law, it's addition law for various cohomology theory. At the moment, I don't want to be more precise here. It is an old paper about formal groups in and spectra of various cohomology theory. If we have P of alpha non-zero, but A2 and A3 0, it means that P of alpha has very, very special expression in terms of these parameters G2 and G3, but algebraic expression with square roots, and rational. Then the group law, it is multiplicative with a coefficient minus Q. This group law, also Buchstaber showed that this group law corresponds to case theory group law. And the corresponding family, it is absolutely shocking for me that this corresponding family gives you a Cayley cubic in affine Cayley cubic in a space of dimension 3. And this Cayley cubic has quadratic term, has this quadratic terms, and this minus Q, sorry, minus Q cubic term. Why it was shocking for me? Because I know this Cayley cubic. I know this Cayley cubic with only quadratic and cubic terms. It obtains by some transformation, which is generalized Braiding group action from Cayley cubic corresponding to Penlevé 6, which we studied with Leonia Chekhov and Marta Mazzocco. In our first paper in 2015, we wrote this transformation, and we have found this cubic, and we call this transformation generalized cluster algebra transformation. So it is very interesting from the viewpoint of dynamics on this cubic, new dynamics which different from usual dynamics on Cayley cubic of P6. But how it relates to all this stuff? So it is a kind of Kontsevich polynomial, finally. Finally, it's a kind of Kontsevich polynomial. And the most interesting, of course, it's the case when A equal to 0 and A2 equal minus G2 over 4 and A3 equal to minus G3 over 4. Then this condition of formal group, special formal group law, it's exactly Kontsevich family with A equal to 0. And it is more or less general fact, because, you know, if you have a cubic, we always have a transformation which can kill the coefficient in front of A. So this is more or less general expression. And B and C, they relate to...
Oh, sorry, in front of what?
Sorry?
Which coefficient?
Coefficient in this cubic F.
Yes.
Look.
Yes, yeah, I just repeat. Kill the
you have this cubic, and you can always kill this.
Yes, so not A, but T square. Okay. Okay.
Coefficient in T square, in front of T square. This equal to 0, you see? And B and C, they expressed like just they proportional to this modular parameter G2 and G3. It's a special choice of cubic, but this special choice of cubic is more or less general, because by change of parameter T, linear change, you can kill this A. You remember how to prove this, what people call Cardano formula for all cubic polynomials. They can consider with the second term equal to 0. Anyway, what we have this Kontsevich family. We have the parameterization X via big X, big Y, and Z. It is X plus Y, and this is nothing but addition law for P function. And addition law for P function is given by 0 locus of this Kontsevich family. And this means that we have the following quartic equation, which relates universally depends on this elliptic curve. This quartic equation gives you, after projectivization, case-free surface. And this case-free surface has 6 A1 singularities and 3 D4 singularities. This I knew from Duca van Straten, who is a big expert in singularities, and he also shared with us this picture. This is a Kontsevich family locus for the formal group law, which corresponding to this surface and to this locus. It's a formal group law associated with elliptic cohomology. And this I don't, I'm not able to comment. Joseph, I think that at this point I should stop.
Okay, well, thanks. You were even shorter than we planned. So let's, preliminary agree on March.
So what I want to finish, because this I just open some card. But I need to explain multiplicativity, and I should speak about absolutely beautiful recent paper of Adesky and Kontsevich, where they gave general formulas for many kernels. They didn't have these beautiful formulas for Bessel and at Bessel, it's our business, but they have not so beautiful but explicit formulas for other interesting kernels. And moreover, I didn't tell why I was interested in, and probably you, I mean, all participants of your seminar, if we are from the viewpoint of integrable systems, we can ask what for all this for integrable systems. And in fact,
well, let's approximately agree for 30 of March, and we shall
for what?
March 30. The last
March 30. Okay.
Yes, yes, and
Joseph, it is okay. Okay, we will discuss with you. Okay.
We'll discuss. Yes, thank you.
I would say for safe side, it would be the next after 30, because 30 March it is very. It might be that I will be unavailable.
Okay, we shall.
We will discuss it with you.
Okay, we will discuss. So, dear colleagues, any questions, remarks?
Yeah,
well,
please.
I would not say that I understood everything. And well,
I want to say that I'm not understand everything. But
yeah,
if
well,
you understand something,
no one understands everything, but well, in in different extents. But okay, well, I would like to ask you.
Sorry, I because I have time. You can ask. You start with some Picard-Fuchs equation which relate to some Calabi-Yau and so on. Why it is relate to what you spoke about? I will speak about it maybe next time in more details. But at the moment, I can say the following: if we take our H2, not H2, H4 Bessel generating function, this one, for n equal to 4. For n equal to 4, this generating function on the diagonal x equal to y, this generating function is a solution of D3 or degree 3 Picard-Fuchs equation, which correspond to Calabi-Yau variety, which I showed you with this quartic. This from the very beginning, I showed you this Calabi-Yau, Picard-Fuchs. This in this one. This degree 3 Picard-Fuchs equation, and its solution, it is exactly well, I'm a little bit cheating, because in fact you have it is not exact diagonal, but as we knew, as we discussed with Duko and Ilya, if we have this H4 xy and we have a slope y equal to alpha to x, for different values of alpha, we will find different Picard-Fuchs equations. If we take alpha equal to 1 on diagonal, we have beautiful equation, but it is not exactly this which correspond to Dwork quartics in P3. What we have a conjecture, and this conjecture is just approved by many computations, that if we take special choice of this slope alpha, we can always recover for any n such solution of Picard-Fuchs equation corresponding to this Dwork type family. So it is a conjecture for any n, and this conjecture is proved for n equal to 4.
Okay, more questions, remarks? Then thank you very much, and hopefully we meet in a week the same time. Goodbye. Thank you.
We should survive, first of all.
Yes, this is the necessary